So hello everyone. Good evening India. Good afternoon Europe.
Yeah.
I'm glad to announce our last speaker of our first Atto Fridays season, who is Dr. Gopal Dixit from Mumbai. Dr. Dixit has finished his PhD from IIT Kharagpur in 2011. Then he joined the Center for Free Electron Laser Science in Hamburg as a postdoc. Subsequently, he moved from Hamburg to the Max Born Institute, Berlin, and currently he is an associate professor in IIT Bombay, Mumbai, India. And he's also a visiting scientist at the MBI Berlin and MPI PKS Dresden, Germany. And during his PhD, he was a visiting student at the TU Munich under the DAAD fellowship. Yeah, also had a DAAD fellowship. They're quite good. And you can see he likes the beach, because if you watched the picture, which we had before, it was taken on the beach. And a lot of our speakers, as you could see from their profile pictures, liked hiking. So Dr. Dixit has decided to send a picture of him on the beach, which is very good, because also it agrees with the fact that this is the last talk of the season. We're going to reconvene in September. And a lot of us, if we're lucky enough, we're going to the beach.
Yes.
Today's talk is going to be a solid talk, and is going to be on high harmonic spectroscopy of different symmetry breaking solids. So Gopal, the floor is yours. Please feel ready to start.
So I hope my slides is visible.
Yes, perfect.
So first of all, thank you very much for your kind invitation and introduction. And let me congratulate to you and your entire team for sustaining the momentum to continue ultra-fast science seminars. And as we were discussing before the actual recording started, you were the first, immediately the pandemic started, to have the online seminar for ultra-fast community quantum battle last year, which was very successful. So many congratulations to you and to your team, Cornelia and Abby. So let me start introducing the topic I'm going to discuss today: high harmonic spectroscopy of different symmetry breaking in solids. And I hope at the end of today's seminar, I will convince you that high harmonic spectroscopy is going to be a powerful tool to understand different interesting processes in solid or condensed matter system. So I will first discuss what is high harmonic spectroscopy. Then I will discuss what is, I'm talking about solid, then I will come to different symmetries. So when you sign, let's say, infrared field to a gas molecules or atoms, these gaseous systems start emitting a radiation, and under a perfect condition, which technically called as a phase matching, you will get a high harmonic spectra, which has typical characteristics like this. And this is the, let's say, the kind of route to get the attosecond pulses. Now, there's an important aspects of this spectra which was puzzling when it had been observed first time, and subsequently for few more years, that immediately after few harmonics whose intensities are continuously declining. So this part can be successfully explained using perturbation theory, but the presence of the plateau immediately convey you that perturbation theory is not anymore applicable, because all the successive harmonics have the equivalent intensity to the previous harmonics, and the perturbation theory breaks down. And this has a peculiar cutoff behavior. In this Atto Friday platform, Maciej Lewenstein, who has played an important role to understanding this high harmonic generation from the gaseous systems and now in solid and nano, has already given a talk. So if you are interested to know more about, please go back and see the YouTube video by Major Clemenstein. Now, to understand why there's a peculiar cutoff and what is the region for the plateau, Paul Corkum and other people have introduced what is called recollision picture of high harmonic generation. So let's say this is your driving electric field of your light. This is your system in equilibrium. This is your Coulomb potential, which is unperturbed. As the field amplitude increases, your Coulomb potential get perturbed, and then there's a possibility that this bound electron can turn it out. And once it's free, then once the direction of the field changes, then it can recombine, and as a result of this recombination, the photon of equal energy is emitted. One of the important aspects of this recollision picture is that as soon as you change the polarization of your light from linear to circular, the probability of recombination drops significantly, and you do not see any meaningful higher order harmonics in the gaseous system when you change your polarization of light from linear to circular. So this is all about high harmonic generation from a gaseous system. And you know, gases are random in space. Okay, now we are going to go from random medium to a periodic medium, where your atoms are arranged in a periodic fashion to form a solid. Now, the first question is that will high harmonic generation occur in solid or not? I believe most of you know the answer because you have probably seen some earlier talks on high harmonic generation from solids. But just for the historical point of view, immediately after 94, 95, when this three-step model and quantum model came into existence, people started trying to generate strong field-driven high harmonics from solids, and they were not successful. And the final success came around 2010, 2011 by Shambhu Gimere in the group of David Rees with the development of the mid-IR laser sources, where they have seen the high harmonic generation from the solid. So this is the results from their Nature Physics paper. And if you see, this is the result from zinc oxide. They do see higher order harmonics up to 17th order or 19th order. This is a particular wavelength. They see even harmonics up to 25th order. One of the surprising things, they immediately see that the cutoff in this particular case is linearly. Okay, whereas in the case of gaseous medium, the cutoff of the harmonic scale with the square of your amplitude, and here it scales with the amplitude of the electric field. Okay, another surprise they have immediately seen that when they change the polarization of your driving laser pulse from linear to circular, they still see the harmonics. You see the dotted line. If you follow the cursor in the slide, they still see the harmonics. So what was going on? And it took almost, let's say, several years to understand the mechanism of high harmonic generation from solids. Okay, and if you are interested to know more, you could go back and watch the talk by Shambhu Gimere, who has given a talk in this Atto Friday forum. So let me come back and start explaining into a simple way. So let's say these are your atoms arranged periodically. The interatom spacing is A. This is a perfectly periodic solid in one dimension. And if you look, this is your typical band structure, okay, under some given potential form. And if you look, this is a band gap at k is equal to 0. And this is your highest valence band, and this is the lowest conduction band. And if you look the high harmonics from this system, which is represented by this energy band, you see this kind of typical spectra. So indeed, few harmonics are decreasing in intensity, and the first cutoff is equal to the band gap, minimum band gap in the solid. Okay, now you see a first plateau, and after the cutoff, you also see emergence of the second plateau. So high harmonic spectra from solid not only exhibit single plateau, but it exhibit multiple plateaus, and people have seen in experiment at least 2 plateaus. Okay, And then the first cutoff is the maximum energy gap between this one, which is shown in the green color. Okay, and then the higher cutoff can be energy difference between the higher lying conduction band to the lower lying valence band, and so on and so forth. Okay, of course, observing so many harmonics are not easy because of the sensitivity of the spectrometer in the experiment and several other factors. So if you look how the cutoff scales with the electric field amplitude, here you could see that this is the electric field amplitude, and these are the photon energy or harmonic order, and you can clearly see that indeed it follows the linear cutoff. Now, to have a underlying mechanism, it is obvious to think solid in momentum space because of the periodic nature of your lattices, the lattice in the solid, and then you immediately apply momentum space picture, and then you have energy band. And so what is happening when you bring intense laser, an electron is tunneled out from valence band to the conduction band, and so you create electron hole pair. Now hole is moving in the valence band, and electron is moving in conduction band, and valence band and conduction band can have a different curvature of their band, so they will move with different velocities. Okay, and when the direction of your electric field changes, this electron can recombine with the hole, and when it recombines, it emits the radiation. So the total high harmonic spectra typically has two contributions, one from the interband combination, okay, and the other one is your intraband motion, where the electron and holes are moving in their respective bands, and both contribute to the total spectra. And now which contribution will be more, which will be less, there is no let's say thumb rule. I mean, there are something that if you see a harmonics below band gap, of course it is going to be mostly dominated by the intraband. But if you are above the band gap, the interband and intraband start playing a significant role. Okay, so now let me come back to the main topic of my talk, the symmetries. So this is a perfectly periodic 1D lattice, okay, with lattice spacing A. And if I look this system exhibits translational symmetry. This system also exhibits reflection symmetry. If I put a mirror at any point, you see exactly the same lattice. Okay, and to just one important point, in 1D, reflection about a plane and inversion about a point could be the same. So in 1D system, reflection and inversion can be interchanged. Okay, so now let's see what is going on. So to introduce first reflection symmetry breaking, what I'm going to do, I'm going to introduce another kind of atom in between the two blue dots. Still, this is a perfectly periodic system. And if you look the potential of this lattice, this is your potential. Okay, and if you draw a plane at this point, still you have a reflection symmetry because this is your one unit cell. And if you draw a plane at this along this line, then still you have a reflection symmetry. And if you look the high harmonic spectra originating from this kind of periodic lattice, what you see a very interesting feature. Indeed, you see a below band gap harmonic, so the intensity is decreasing. Then you see a first plateau, and then you see a second plateau. Now this second plateau has a minima. This has a dip, and these are the results with different driving intensity. And you see that the dip is not moving. Of course, the position is fixed. However, the strength of this dip is changing with respect to the intensity. Okay, so to have a more understanding, what we did, remember that reflection symmetry is preserved in this particular periodic system. Now, what we have done, we have looked the position of your minima with respect to the intensity. Indeed, it is constant. This error bar is the width of your minima. This is also kind of constant with the potential depth V0. However, this minima, position of the minima is changing with respect to the lattice constant A, which is this one. And this is also changing with another parameter, alpha star. And let me tell you what is alpha star. Alpha star is the depth of this versus depth of this. It's given in this our work, which we have published in Physical Review. So indeed, this minima is sensitive to the system property, but it is insensitive to the ledger properties. So it is a structural minima. Okay, so that's what we call this as a structural minima. And what we have found that this minima has the similar origin what people have seen in the case of molecules, which is called as a Cohen-Fano minima in molecules. Now, coming back to the symmetry property. So what I have done now, I have introduced some kind of bias so that this well or this depth has been asymmetric. If you draw a line, now this is not anymore symmetric with respect to this green line. Okay, and if you look the high harmonic spectra, you see that the minima is gone. Okay, so once you break the reflection symmetry in this particular setup, the minima is gone. The reason is simple, because what is happening, the wave function is localized in one particular well and not to the another well. And now when the electron is gone, then it can only recombine to one, not to the other. And then the source of interference or equivalence between the two lattice point is gone, and that the region there is no minima. This paper also introduced in 2019 that instead of thinking this electron-hole recombination in momentum space, you can indeed think electron-hole recombination in real space, which is equivalent to the three-step model what Paul Corkum has proposed for the high harmonic generation from the gaseous system in real space. So that was all about reflection symmetry. Now I can remove one atom and then I can break easily translational symmetry. Okay. Now what will happen? Once I have done it, I can remove this bit different concentration. So I can have 3 atoms. So here you could see 1, 2, 3, 4, 5, 6, 7. Out of 7, I have removed 1 atom. So you can see what is the percentage of my vacancy. So this is a typical case of vacancy in solid. Okay, and you could see that this is the pristine band structure which you have seen earlier. And now, as you have 4.7% of vacancy, you can see that this effective band structure starts showing some kind of degeneracy lifting. So the band structure starts showing some kind of branching, and you keep increasing, you start also seeing some kind of localized energy level, which are also a signature of your defects level here. And if you keep increasing, it become more like a LOI kind of things. Okay, so let's see what it is going to have effect on your high harmonic spectrum. So this is the high harmonic spectra. So the green line is the pristine, where your translational symmetry is preserved, and the red line is the one where you have broken the symmetry by removing 1 atom. Okay, and if you zoom the below band gap region, and if you see what looks like, then you can see that this is the first harmonic, this is your third harmonic, and so on and so forth. And then you start seeing some kind of additional peaks and all these things. The reason could be attributed to the transition to these additional states, and that are leading to a different high harmonic spectra in the case of vacancy. Now I will come to into detail in a later part of my talk. Okay, now let's see. So you can see this dotted line, which is the perfect periodic potential. Okay, now you could remove 1 atom. So this is a vacancy. Instead of that, you can also do a doping, and as an effect of the doping, if you have overdoped or underdoped, the depth of your potential can be shallow or can be deeper, depends on what kind of doping you have. And if you look the effective band structure in all the 3 cases, so this is for the vacancy with the same concentration, this is the overdoping with the same concentration, and this is the underdoping with the same concentration, and you can see that the band structure in all the three cases are remarkably different, and so they will show a different signature to the high harmonic spectra. I will not go into detail because I have to move to another interesting topic. If you are interested, you could look to our publication of 2020. Now, till now, I have discussed the case of model systems, which is limited to, in our case, to 1D. So I want to go from model to the real system, and I also like to transit from 1D to two-dimensional. So, and in this case, first I will discuss the breaking up the translational symmetry, which is the continuation from 1D to 2D. So to exhibit this particular effect, what I did, we took hexagonal boron nitride. So here is your boron and nitrogen, boron nitrogen arranged in a hexagonal pattern. And this system is a two-dimensional material, and it is kind of insulated in the band gap of around 6 eV. Okay, and if you look the high harmonic spectra coming out from the pristine, which is shown in the green line, and now what I can do, I can remove one boron atom, which is the high harmonic spectra from the boron vacant HB, and is shown in this darker reddish color, brown color, whatever you could call it. And you could see that this is a very different high harmonic spectra. Now, again, I will zoom the below band gap region, and you could see that you have a drastic enhancement of the third harmonic area. Okay, and of course, other part also that I will discuss in a later part of my talk. Now, what I can do also as a computational physicist, I can also resolve my total high harmonic spectra originating from boron vacant hexagonal boron nitride. I can resolve into the spin channel. So this color is for spin down, and the green color is for spin up. And if again I zoom it, I again see that spin down channel is contributing a few orders of magnitude more than the spin down channel, spin up channel, sorry. Okay, and the higher energy part of the spectra are pretty much consistent. Okay, now instead of boron, I can also remove nitrogen. So this is the spectra originating from nitrogen vacant hexagonal boron nitride, and you could see that again I can zoom the band gap, below band gap region, and I can again see that the third harmonic is enhanced drastically. And I can also analyze my spin resolved harmonic spectra, and here you could see that the spin up channel is contributing much more than the spin down channel. So now the trend is reversed. Some of the observations are consistent, and here also you do see that some parts are different even at the higher energy part of the total harmonic spectrum. Now to understand the whole procedure, what is going on, what is the physical observables or physics making all these differences in harmonic spectra, due to the time limit, what we have seen, electron-electron interaction is very crucial when you are going to talk about defects in solid. There is something called local field defects. I will not discuss in detail. And there are something called localized defective states. All are playing roles in the high harmonic generation from defected solid. So let me focus on one thing which will give you some qualitatively understanding why the third harmonic is enhanced and why one spin channel is contributing more than the other spin channel. So if I analyze the effective band structure for the boron vacant hexagonal boron nitride, and then I analyze spin up and spin down channel, and this is the band gap region. And if I zoom it from the spin up channel, what I see a localized defective state, and there is only one localized defective state here. Whereas if I zoom the same here, I do see two localized defective state in the case of spin down channel. So indeed, if you have a more defect states, they are going to contribute more. And that's why you are able to see that spin down channel is contributing more in comparison to the spin up channel in case of the boron vacant HPN. Moreover, these defect states are in between the band gap, and that's why the higher order harmonics spectra are very different in the below band gap regime in HPN as well as in boron vacant HPN and nitrogen vacant HPN. Okay. Now let me give a even more simple reason why this is happening. So think about it. You have boron and nitrogen arranged in a hexagonal fashion. Now, when you remove a boron atom, what you are going to do, you are going to have one extra electron in this hexagon because nitrogen has one extra electron, one electron more in comparison to the carbon, and boron has one electron less in comparison to the carbon. So then this extra electron will not kind of equilibrate the chemical vacancy, and that's why you see some kind of spin resolved fashion. For if you have a quantization x is fixed, then let's say in nitrogen case, if it is a spin up, then in the case of boron, it's spin down, and that's how this is playing an important role. So what we have seen that if you create a vacancy in HPN, and if you remove either boron or nitrogen, indeed you see a drastic change in the high harmonic spectrum. Also, this spin resolved high harmonic spectra are also different in the two cases. Let me make an important observation in this work. So this work we have published in 2020. In this work, what we have also speculated, instead of removing, if you substitute boron or nitrogen with the carbon, which is the favorable doping, then what will be the qualitatively effect on the high harmonic spectra? And instead of going to the mono vacancy, we have also speculated what could be the effect in the high harmonics when you have a bi vacancies and so on. And we have also calibrated our results with the vacancy concentration. So we have gone from 5 cross 5 to 7 cross 7, almost 100 atoms in supercell, time dependent calculation. And I'm proud that this is one of the best calculation one can do when it comes to the vacancy defected solid and high harmonic generation. When we started our project, I think in 2018 or something like that, late 2017, there was not a single paper on this topic. By the time we finished the project, there were already 2-3 papers using the model Hamiltonians and investigating what could be the possible effect of the different kind of defects in the high harmonic spectra and all this thing. But this is originating from the realistic material where high harmonic generation from HPN can be done easily, or people have done it, and what could be the role of electron-electron interaction and other important findings. Now, let me move on from translational symmetry to the inversion symmetry. Okay. As I told you, in 1D linear chain, plane of reflection and point of inversion could be the same, but this is not true in case of two-dimensional system. So let me give an example. So this is my graphene, and graphene is known to have inversion symmetry because all the carbon atoms are identical. Okay, and if I take equivalent to the material like gapped graphene, which I have shown earlier, let's say, gapped graphene. So this could be hexagonal boron nitride or any kind of transition metal dichalcogenide, MOS2, MES2, whatever material, they have inversion symmetry broken, okay, because of different atoms arranged in a hexagonal fashion. Okay, so I'm going to focus this particular study on graphene. Okay, so let me come to the graphene. So graphene in inverted symmetric. So how to break this inverted symmetry? So what we are going to do from our previous experience, we are going to employ bicircular field. What is the bicircular field? Bicircular field is composed of counter-rotating circularly polarized fields with frequency omega and 2 omega. And if you look the total electric field for one cycle, it shows three-fold symmetry. Okay, and if you vary the subcycle phase between the two light fields, then you see that how this three-fold flower is rotating, and after phi is equal to 180 degree, it return back to the original case. Okay, and our results, what I'm going to show, is insensitive to whether your omega is counterclockwise and 2 omega is clockwise or vice versa. So what we are going to do, we are going to sign this bicircular field to the graphene. So let's say this is my graphene, and graphene has two equivalent minima, K and K prime. And if this field is put at this edge, then it is going to address equivalent the three neighboring atoms. And this is the energy contour. So you could see that at this minima, energy minima, which is also known as valleys, this fits nicely with the energy contour, whereas for the another equivalent minima, K prime, this does not fit. If I change my phi from 0 to 90 degree, then it will address to the K prime value, but it will not address to the K value. Okay. And if you want to know more about this bicircular field and different kind of symmetries in atoms and molecules, please watch the talk given by Professor Milosevic in this Atto Friday platform. Okay, so what the outcome of this bicircular field in the graphene? So let's see. So this is my real space. This, when it is addressing this, it addresses all the three neighboring B atoms, B-type carbon atoms equivalently. Where you rotate it, the symmetry is broken. And this creates what is called a valley polarization. So let me define what is my valley polarization. So valley asymmetry parameter. Our valley polarization is defined as the difference of the valley polarization in the two valleys, K and K prime, normalized with the mean. And you could see this valley polarization for different subcycle phase and different laser intensity. So for moderate intensity, you don't see any valley polarization, but once you exceed some critical value of your laser intensity, you start seeing significant valley polarization, valley asymmetry between the two values. The reason is simple. Let me come back to this contour to explain it. So if you have a relatively low intensity of laser, so the near energy regime of this K point are isotropic. So you don't see any difference between the K and K prime values. But once you exceed a critical value of your laser intensity, then you get more force, and then the electron start experiencing asymmetry of the two values, and that's why the valley polarization is coming up. Okay. Now, what will happen to the high harmonic spectra? And it is known that in the case of omega to omega driven system, due to the conservation of angular momentum, you do see no harmonics at 3n, which is the n is the number of harmonics. So 3n, 6n, 9, 3, 6, 9, and so on. You only see 2n plus 1, 2n plus 2 in that one. So you see first, second, fourth, fifth, and you can immediately recognize that once you have a second harmonics or fourth harmonics, or you could say that the presence of the even harmonics, a kind of hint that the inversion symmetry is broken. Okay, and these harmonics also exhibit different kind of polarization. So this shows left circular, and the blue are polarized with the right circular field. Now, how the harmonic yield will change if you start showing if you start changing the subcycle pulse. So you can see that this is my fourth harmonics. It shows periodic oscillation. This is my fifth harmonics, and they say the same maxima and minima. This 6 is absent, third is absent. You can also see the 7th, you can also see the 8th. But important point is that if you resolve these harmonics in either K or K prime valley, then you can see that when K valley is contributing, K prime valley is contributing nothing, and vice versa. So this harmonic yield is either coming dominantly from K or K prime valley. So the high harmonic spectra encode the valley polarization if you analyze with respect to the subcycle as a function of subcycle. So this is the inversion symmetry breaking in graphene. And what is the consequence of this if you see a valley polarization or valley asymmetry between the two valleys in graphene? So let me briefly go and see and say what it is. So let's say you have hexagonal material. As I said that in the case of HBN or transition metal dichalcogenide and other similar systems, and the two, first of all, they are all non-zero band gap material. That's why they called as a gapped graphene kind of system. So they have a band gap, and these two valleys can be selectively connected or addressed using a different kind of polarization. So the K valley can be selectively excited from valence band to the conduction band using sigma minus, or K prime can be selectively excited using sigma plus valley. And this valley selective excitation form the basis of Valleytronics. So what are the Valleytronics? So this additional degree of freedom valley can be treated as valley pseudo spin, and these value pseudo spins have the potential to encode and store the quantum information. So there's a very interesting work going on how to use Valleytronics for different kind of quantum computation and realizing different kind of logic gates. Okay, but this is not true in the case of graphene, because due to the inversion symmetry, K and K prime values are equivalent, and because of zero band gap, this kind of scheme cannot be employed in the case of graphene. So if you read any paper till 2021, all the papers write first line that pristine graphene cannot be used for Valleytronics, okay, because of K and K prime values are equivalent and zero band gap, so there cannot be any kind of resonant excitation. Okay. However, there are efforts, and people have reported how to break inversion symmetry in graphene. So what you do, you form what is called a super lattice or heterostructure. So you put a graphene layer on top of HBN, for example, and due to lattice parameter mismatch, you create a band gap. That is one option. Other option is that you can apply a strain, and then you can create a symmetry. Okay, and in all the cases, you are kind of doing a mechanical or permanent damage to the system. What we have proposed in this case, this is a transient symmetry breaking in graphene, transient inversion symmetry breaking. And once the light pulse is over, you are back to the inversion symmetry graphene. Okay, as I said, that is so. This is the most of the papers say that with the zero band gap and total zero valley curvature and analytical dispersion near the bottom of the two valleys, pristine graphene appears unsuitable for Valleytronics. By the way, the transport properties in pristine graphene is more prominent in comparison to the any other gapped graphene kind of system. So what we have shown in this work, which we have published in Optica in this year, that using this bicircular counter-rotating field, inversion symmetry can be broken. Okay, I don't know how I'm doing, but let me come to another very, very important aspects of condensed matter or solid. This is something called Majorana Fermion. Majorana Fermion is kind of proposed by Atto Majorana almost like 60, 70 years back. These are the particles which are their own antiparticles. And in last, I would say 20 years, there are series of experiments and theoretical work to see the signature of Majorana fermions. But till now, there is not a single conclusive evidence that indeed they have seen the signature of Majorana Fermion in any kind of experiment. So the notion of Majorana Fermion is of great importance not only in condensed matter but also in nuclear and particle physics. One of the reasons in condensed matter are recent interest to see the signature of Majorana fermions, because these things have been proposed to realize qubit and fault-tolerant topological quantum computation. And there are a set of experiments done till date, but all these experiments are based on by measuring the transport properties or doing some scanning, tunneling microscope kind of experiment. What we have proposed in this work, that we can use this kind of intense ultrashort light to probe the signature of Majorana fermions. Due to the limitation of the time, I would not go into detail, but I would suggest those who are interested to read the entire story, please look this paper. Of course, a lot of things has been updated, but this paper has the main concept and important results, which without any doubt show that using high harmonic spectroscopy, you could see the signature of Majorana fermions without doubt. What we have done in this work, we have used a Kechaev model in one dimension, and in this particular work, there is no symmetry breaking, but what is not conserved is the number of charged particle. So this is another aspect. So I think with that, I don't know how I'm doing, but let me conclude. So this is the take-home message. So you have a periodic 1D lattice. What I have convinced you that instead of this, if you take the bichromatic periodic lattice, you have a reflection symmetry preserved, and once you introduce some kind of bias, you could see the signature of reflection symmetry breaking. Then you could remove atom, or you could put some another atom, so you could break the translational symmetry, and you could also see some signature. Now you can move from model Hamiltonians to the realistic material, and from one dimension to the two dimension. And what we have shown that you can see spin polarized high harmonics originating from spin polarized defects in hexagonal boron nitride. And in the last, I have shown that using this bicircular field, you can break the inversion symmetry in pristine graphene, and as a result of this breaking up inversion symmetry, you can see Valley polarization or Valley asymmetry. So K prime goes a smaller contribution and K gives more, or vice versa. Okay. With that, I would like to thank you very much for your kind attention. The graphene work, we have collaborated with the MBI group led by Misha Ivano. And for HBN, because we have used Octopus for real-time TDDFT calculation, where one of my group member, Mridul, who has just submitted thesis, has contributed in code writing or extension of this code. So we acknowledge Uncle Rubio and Nicholas for HBN work. And thank you very much. This is an old picture of my group. Thank you.
So thank you so much for this really nice talk. Are there questions, comments? So before we start, I'll release a poll so that we can know where you're joining from. And I'm going also to make a few announcements. Namely, we have a special issue of European Physical Journal G, focused on the quantum aspects of Atto science. If you would like to contribute, drop us an email and let us know. It's growing strong, and you still have a chance to contribute. So do let us know. Drop us an email at Quantum Battles, or drop me an email and say, okay, we would like to contribute, and give us a tentative title and a tentative in a tentative time frame. And it seems today that we have quite a lot of people from elsewhere, which I don't know actually where it is, because we see we have from Canada, Asia, and many people from elsewhere in the poll. And another announcement is that we have we are planning our 2022 Atto Fridays, and we're going to introduce hot topic sessions, which are focused on early career researchers. So if you would like to give a talk and you would like to contribute and are an early career researcher, drop us an email, and you find the instructions about the hot topic sessions in our Quantum Battles website. So I don't see any questions here yet.
Carla,
People
I think
are busy to go. I mean, I'm standing in between their vacation because this is the last talk, and it's a Friday, so people are planning to go for a vacation.
No, but there are enough people. They should ask questions.
I think you could have another poll whether they're watching or attending this talk from their home or offices or from some beach or bar.
Yeah, we should. Let me stop this. I mean, it seems that we had some people from elsewhere when I launched the poll that I didn't really understand.
Carla,
Yes.
Europe isn't an option.
Huh?
Europe isn't an option on the poll.
Oh my God, I forgot.
So elsewhere's Europe.
Ah, brilliant. I forgot Europe. Okay, my fault. I thought, okay, these people are from Mars, but you are right, it's from Europe. Yeah, I'm also from Europe. It's like like when you are almost close to your holidays, you know. This is true actually. But you talk about vacation. I'm gonna launch this one.
Yeah.
To see, but please ask the questions. This poll is just to break the ice. So, what are you going? A lot of people going to the beach. I don't know where I'm going. Trek in the middle of nowhere. Some people and working on the lab. Tahir, Sharon would like to ask a question. Thank you for your talk. Do you consider macroscopic propagation on your calculations? Also, do you see any symmetry break between odd and even harmonics?
We haven't included any kind of microscopic propagation in any of these simulations. I don't understand what is the second question. Do you see any symmetry break between odd and even harmonic? What it mean?
Tahir, would you like to unmute yourself and talk to
Okay, Carla, thank you very much for your nice talk. It was a great work. I really enjoyed listening to the talk, and for the work you've done, it was very good and great. What I mean by the break of symmetry in odd and harmonic, because in like a plasmonic system, as what the study I did like 8-9 years ago, we see the break between odd and even harmonic, and we observe in that kind of system even harmonic too, which is predominant. We have both even and odd harmonic in our spectrum. I just wondered to know, in your system, did you look at that kind of things? Because in some of the spectra I saw, especially at the low harmonic, you have kind of signal of even a harmonic, but I just wanted to know in this kind of system, is it important to look at this symmetry break between this different harmonic? And that's one thing. And then on a first question about the macroscopic propagation, because I believe in terms of experiment from experimental point of view, if you want to have this kind of harmonic in this kind of system, this propagation part plays a very significant role, because then the intensity or the signal we getting at the end of the day is in the experiment aspect is very important. If you could comment on that, I would be very pleased. Thank you.
Thank you very much. Thank you for your kind compliment. First of all, I'm aware about the plasmonic work that you have done, not one, but series of papers you have written. Now, in the case of the plasmonics, you see your electric field becomes space dependent. And this, you can take the space dependent as you have done in some of your papers, like either linear in X, or you can have a polynomial expansion or any other kind of thing. And then you break the inversion symmetry, and then you see even harmonics. The same we are seeing here. For example, in the case of graphene, we have broken the inversion symmetry, and immediately we start seeing what you see even harmonic. If you have a pristine graphene, no bicircular, only linearly polarized driver, you can only see odd harmonics. And that has been seen two set of experiments, one from Japan, 2016-17 science paper, and then there is another follow-up paper by Paul Corcoran, group by Marcus Tucker in the first author. Now coming to propagation effect. To my best of knowledge, unlike in gaseous medium, in solid, propagation effect does not play that much of significant role because phase matching is not a crucial issue here. And starting from the first result till recent so-called topological paper came out in Nature maybe a month back from Regensburg group, the simulation done at a solid topological insulator without including propagation effect explains all the observations made in experiment. So yes, indeed, there are work, for example, from Joachim Burgdorfer from Vienna, who have included the propagation effect. I think there's also work by Vladimir Yakovlev, Vlad from MPQ, but most of the works, to my knowledge, when it comes to the comparison between the theory and experiment, propagation effect is not that important. Indeed, we wanted to do in future sometime, but we will see how these results will change when we will include it. But right now we have not added. I hope I have answered your question. If not, then please ask further.
Is that fine, Tahir?
Thank you. Thanks. It's clear now. Thanks.
Thank you. So we also have
Hello.
Sanavas Alam who would like to speak. Yes.
Yeah. Hello. Thanks for the great talk. I have a very basic question. So what is the role of this vacancy in HBN and how it is created? And my second question is, what are the phase matching conditions? Can you please explain it?
Okay, so let me come to the first question. So the role of the vacancies, at least the mono vacancy, let's say, your energy band structure becomes spin polarized. So theoretically, you have ability to look the total band structure only for spin up electrons or only for spin down electrons, and once your what you say band structure becomes spin polarized, your high harmonic spectra will be different for spin up and spin down, because there will be additional energy level which will help to promote the electron from conduction, from valence band to the conduction band. So these paths will interfere and the below band of harmonics will be enhanced. And once you have bivacancies or cluster of vacancies, then one need to look how the band structure will look like, and then what will be the effect, which we have not done because the limitation of the computational resources. This was even challenging to us. I mean, I would say very challenging to us, this one. What was the other question? Sorry.
What was the other?
Yeah. Oh, what are the phase matching conditions?
Here, phase matching condition had not included, as I have answered in the previous question that propagation effect is not taken into account. So it's at the solid slab level calculation, no propagation.
Thanks a lot.
Okay. So is there any further question? Anybody would like to ask something? Do feel free to ask. And for those who asked about vacation, I'm sharing it quickly, as you can see. Yes. So
no need to work in the lab.
Exactly. People, there is something like work-life balance, but at least second is beach. I'm going like, for me, it's a coherence per position. If I manage to go through all the checks, which are going to be beach and trekking in the middle of nowhere. But the chair cannot vote. And nobody really is into locking myself in a tower with no internet access. Currently, I'm in a tower with internet access. So I think it's boring for people. So I would really like to thank Dr. Gopal Dixit for his really great talk. And also, we're going to have a round of applause.
Thank you very
much. It's the best I can do. It is for all speakers in this season of Atto Fridays. We're going to go somewhere or do some staycation. And this is the last talk before the holidays. So we'll be back on the 10th of September. But for the moment, we'll go to the beach. And thank you all on YouTube for watching.